In this video, we're going to see how to draw Lewis structures for molecules involving covalent bonds. In the last video, we saw how to draw uh, Lewis dot structures for ionic bonding. But here we're going to see how they share electrons following a series of rules. The series of rules can be found in your note handout, as you see here. There's also a great video that details drawing Lewis dot structures over here, which is a different perspective that you can watch as well. So here we have the list of rules for drawing Lewis dot structures. I'm not going to read every single one. I'm rather going to go through them as examples, through some examples, and show you the rules as we go through the examples. But I do want to define a few terms. So when we're drawing Lewis dot structures, you do need to familiarize yourself with the terms that we described in the previous video, molecular terminology. So please make sure you do that. Typically, you're going to have a central atom. So suppose we have a molecule like this. Let's say carbon tetrahydride, or methane, we call it. Notice there's 4 hydrogens and 1 carbon. The central atom is usually going to be the one that's less electronegative, but oftentimes in a molecule like this, it's going to be the one that there's less of, because the other atoms will bond around it. So this is going to be the central atom, and then the hydrogens will be the surrounding or peripheral, or we call them outer atoms as well, that are connected to the center carbon. So we have our central atom, which is the one in the middle, and the peripheral atoms, which are the ones on the outside. And the idea is that you want to make a structure so that all the elements are happy. In other words, they have their full valence shell. What you're going to notice is that for an element like hydrogen, it's only going to need one bond, one line all the time, because it only needs 2 electrons to fill its valence shell. But things like carbon, nitrogen, oxygen, fluorine, they need a complete octet. They need to have 8 electrons to complete their valence shell. There are a few other tips that we'll pick up, but essentially, if you have carbon-containing compounds, usually carbon is going to be that central atom with everything connected to it. If you have oxyacids, we'll take a look at some examples later on, the hydrogen is going to bond to the oxygen in the oxyacid. And so from the review, you would know what an oxyacid is, but like I said, there'll be an example later on if you did forget. So the idea is that you're going to draw a structure that satisfies the octet, or the full valence, for each element in that compound. There are some exceptions. You can sometimes have what's called an incomplete octet, where the element actually doesn't need to have a full valence shell. The main exceptions for that are the incomplete octet of beryllium, Be. It only needs 2 bonds, so it doesn't have to have 8 valence electrons. And also the incomplete octet of boron. This only needs 3 bonds. So 6 valence electrons. So these are some exceptions, and we're going to take a look at these examples as well. And there's also some elements that can have actually more than 8 electrons in their valence shell, based on the model of the atom that you're going to learn about in grade 12. So you can have more than 8 electrons in the valence shell. So let's just take a look at some pictures below here before we start drawing some examples, just to see what we're dealing with. So here we have various Lewis structures. Here we have the Lewis structure for ammonia. And what I want you to notice is that the nitrogen is the central atom. It has 1 lone pair, and then we have 3 bonded pairs, 3 single bonds between the 3 single bonds, so between the nitrogen and each hydrogen. The central atom, it follows the complete octet rule. It has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons, 2 from essentially each line, and then 2 from the lone pair there. And the hydrogens are happy because they have their 2 from the bond. Now, let's take a look at this example over here. Here we have all the surrounding atoms are chlorines. And if you count, you'll notice they all have 8 valence electrons, so that works. But take a look at the central atom, phosphorus. It has 1, 2, 3, 4, 5 lines, 5 bonds with 2 electrons each. That's 5 electrons times 2 per bond. That's 10 electrons. So it has an expanded octet. Let's take a look at this one here. This is boron trifluoride. You can see the fluorines are the surrounding atoms, and boron is the central atom. The fluorines each have 8 valence electrons, so they're happy. But you'll notice that boron has only 6 valence electrons, and this is the complete structure. This is the correct complete structure for boron trifluoride. So we're not dealing with an expanded octet here, but rather we're dealing with an incomplete octet. So this one here was expanded, and this one here was incomplete. And so you should familiarize yourself with the exceptions of beryllium and boron being incomplete octets, and also understand that you can have expanded octets, and that's usually from the third row going forward. So if we look at our periodic table, everything in the first and second periods need to have their complete octet, except for your exceptions, beryllium and boron, but carbon, nitrogen, oxygen, fluorine, they need to have those 8 valence electrons. But once you get to the third period, things like phosphorus, sulfur, for example, even things like xenon down here, they can have more than 8 valence electrons, so you can have expanded octets. So if you're in the second period, your central atom should never have more than 8 valence electrons. But once you get to the third period, your central atom can have expanded octet. So just remember that in the exceptions as we go ahead to draw Lewis structures. So let's do an example together. We'll start off with CCl4, carbon tetrachloride. Our first step is to count the total number of valence electrons in the compound that we have to spread out. So carbon we know is in group 14, so it has 4 valence electrons, and chlorine has 7 valence electrons. Now, to find a total number of valence electrons, it's going to be 4 for carbon plus 7 times 4 chlorines, because there's 4 chlorines there. And that's going to be equal to 32 electrons. So what that means is that there's 32 electrons to place around all these atoms, and each of them has to satisfy their complete octet. So we're going to place our central atom first, which is the one that we have the fewest of in this case. So carbon, when you have carbon, it's usually a central atom. And we're going to put our surrounding atoms around it with single bonds. So I usually start by placing my surrounding atoms around the central atom with single bonds first. And so what you need to realize is that what you've actually done is you've placed electrons from these 32 into this picture already. You place 8 electrons because each single bond counts as 2 electrons. So what is there left to place? Well, 32 minus 8, 24. And so what we do is we start placing those electrons around the peripheral atoms until they're all happy. And then we can go ahead and place them on the central atom until it's happy, if needed. So for chlorine, we need 8 valence electrons. We already have 2 from the bond, so 1, 2, 3, 4, 5, 6. 6 are placed. We have 18 left to place. Let's go try it here. 1, 2, 3, 4, 5, 6. So total of 12 are placed. We have 12 more left to place, and it looks like we can place those on our chlorines to make them fully happy. So our chlorines are all stable, so we just placed 24 here, 0 left to place. They all have their full valence shell. Let's just make sure our central atom has our full valence shell. So carbon has 2 from the top bond, 2 from the bond on the right, 2 from the bond on the bottom, 2 from the bond on the left. Carbon has 8 as well. So we ran out of electrons, and that's okay because our carbon's happy and so are our chlorine. So this is a nice complete Lewis structure for carbon tetrachloride. Carbon does not have any does not have any lone pairs. It only has bonded pairs connected to it. And so one thing you might notice as we go throughout this process is that you'll notice carbon typically will have 4 things connected to it most of the time, unless you have a weird ion of some sort. But most of the times it's either 4 single bonds, or for example 2 double bonds, or you might have a triple bond and a single bond. So something along those lines there is what you'll typically see for carbon. It has a valence of 4, which means it can connect to 4 things, or connect 4 times. So let's take a look at another example. You can pause the video and try it yourself. So in this case, we have H2O. I'm going to start off by counting the number of valence electrons I would have in this molecule. So 1 for hydrogen, since it's in group 1, and 6 for oxygen, since it's in group 16. So total would be 2 times 1, because there's 2 hydrogens, plus 6. And that would be 8. 8 electrons a place. So our central atom is going to be oxygen. There's only one of it. And we're going to connect the hydrogens to it using single bonds. And so what we've done is we've placed 4 electrons already, 2 in one bond, 2 in the other. So minus 4, that means there's 4 electrons left to place. So we can go place those around the atoms that are not happy yet. Now, hydrogen's already happy. It can't have an expanded octet, so you can't go add lone pairs onto that. But oxygen is not happy yet. It only has 1, 2, 3, 4 electrons. So let's go and place those 4 electrons on the oxygen. 1, 2, 3, 4. Now we've placed all the lone electrons and everything is happy. 2 for each hydrogen, 8 for oxygen. This is our Lewis structure for water. The electrons are technically placed incorrect. I did pair them, which is good. But later on, we're going to take a look at something called the VSEPR chart to tell us the shape. We're going to worry about this column right now, but in the next video, you'll see that these Lewis structures are really a 2D representation of the molecules. Molecules are actually 3D, and so we can use VSEPR to draw the 3D shape and place the electrons in the right way. We'll worry about that later on. For now, this is an okay Lewis structure for water. So far we've seen examples with only single bonds. We've seen the central atom being happy every time, either by having only single bonds or by having single bonds and lone pairs. Oxygen, for example, here has 2 lone pairs and then 2 bonds. Let's take a look at an example where we have a double bond. Let's take a look at carbon dioxide. So everything is essentially going to start off the same. We're going to have, let's count your number of valence electrons. So there's 6 for carbon, 8 for oxygen. So 6 plus 8, but don't forget there's 2 oxygens. So that's going to be 22 electrons to place. So we'll start off by drawing our carbon and connect it to our oxygen atoms by single bonds. Carbon is central because there's only one of it. And so that means I place 22 minus 2 bonds, so 4 electrons, which is 8. I've placed 4 electrons, so there's 18 left to place. So I'll start by putting them around the peripheral atoms until I am until they're all happy. So let's take a look if that works out. So we have, oh no, I think I made a mistake there. Carbon is not 6. Carbon is, I realized my math was off. Carbon is 4 because it's in group 14. And so that's 4 plus, and then I also messed up my oxygen there. So if you were confused, that's okay. That means you know that I made a mistake. So 4 and 6. So plus 2 times 6, that makes more sense. There you go. So 4 plus 12 is 16. Okay, now it makes sense. 16 minus 4 electrons placed, that's 12. 12 left to place, so let's go ahead and do that. So 1, 2, 3, 4, 5, 6. This oxygen's happy. I placed 6, 6 more, 1, 2, 3, 4, 5, 6. That oxygen is happy as well. So we've placed all our electrons, our oxygens are happy, but we got to double check our central atom. Notice carbon only has 1, 2, 3, 4. So it's not happy, and we ran out of electrons. So if we go to our steps, we essentially did everything right. We did our central atom, we found a number of total valence electrons, put our central atom down, connected to peripheral atoms by single bonds, subtracted the 2 electrons per bond. We distributed the remaining electrons until everything got a stable octet. But notice that the central atom could not get a stable octet, and we ran out of electrons. So when that happens, we want to create some double bonds and triple bonds if possible. We're going to start by seeing if we can create double bonds first. And if we need triple bonds, we can go ahead and do that afterwards. So let's go over here. You'll notice that we need to essentially have double bonds on our carbon. And where do those double bonds come from? Well, they come from electrons that you already have. In other words, we're saying, okay, carbon is not happy. Oxygens, you got to contribute a little bit more to the share here because you're only contributing 1 each. So this oxygen could contribute those lone pairs and create another bond there. And so if we did that, we would have 2 bonds, carbon. And you'll notice you'll have 1 bond, that's still only 6. So this oxygen can still contribute as well. And we have this, this, and this. So now, whoops, let's draw that so it's a bit neater. So now our oxygens are still happy. They have 1, 2, 3, 4, 5, 6, 7, 8. Same thing with the other oxygen on the other side. And our carbon has, well, 4 bonds total. So there's 2 in each line, which means that there's 8 electrons on the carbon now. And so now everything's happy, and we have our Lewis structure for carbon dioxide with that double bond there. So if you run out of electrons before your central atom is happy, you need to create double bonds, unless, of course, you have one of those exceptions, the beryllium or boron. Let's try a triple bond example. So here we have Cn minus. So same idea, except you have to pay close attention. There's a rule here. If you have a negative charge, you need to make sure that you're adding electrons for that negative charge that's there. So whenever you have a negative charge in your ion, be sure to add electrons. If it's -1, you'll add 1. If it's -2, you'll add 2. -3, you'll add 3. Okay, so make sure you add that to your valence electrons in your count. So here we have 4 for carbon, 5 for nitrogen, 1 from the negative charge. And so we're going to have 4 plus 5 plus 1, and we get 10 electrons a place. So let's go ahead and connect our atoms. There's not really a central atom here, like that. Actually, I'm going to draw them a little bit higher up because I'm going to have to do a couple steps here because we know we're going to have a triple bond. And how do you know if you have a triple bond or double bond? It's really just if your central atom or one of the atoms is not happy, unless it's one of the exceptions, you have to create those bonds. So we connected them by one line, and so it's going to be 10 minus 2, which is 8 left to place. So let's go start filling out any atom. We'll choose, let's just say we're going to fill out nitrogen. So we have 1, 2, 3, 4, 5, 6. That's happy. Let's go on the carbon. 7, 8. And we're out of electrons. So we're out of electrons, and you'll notice that 7, 8. You'll notice that carbon is not happy currently. So we're going to create some bonds. So what we can do is we can grab a bond from the nitrogen here and make it share a little bit more. And if we do that, we get double bond like this, and like this. So we're still a little bit off. You'll notice that carbon has 1, 2, 3, 4, 5, 6. And it has lone pairs on it still. Nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen's still happy. It's trying to help carbon out because it was able to switch some of its lone pairs into multiple bonds. But carbon's still not happy. It needs a bit more help. So what we can do is, if you put the lone pair from carbon in, you'll notice that won't make carbon happy because carbon will still have 6. So it's still saying, nitrogen, can you help me out a bit more? I need a little bit more a bond of electrons from you to have my complete valence shell. So nitrogen says, yep, sure, why not? And now we have a final structure where we have a triple bond here. And then we have our lone pairs back on our carbon there. So everything's happy. Carbon's happy. Nitrogen's happy. We have a triple bond in there. Now, since this is an ion, we have to put brackets around it and put the charge, -1. So when you're counting your valence electrons, if you see a polyatomic ion, you need to make sure you add the number of electrons that corresponds to that negative charge to it. If it's a positive ion, you take away the number of electrons from your valence electron based on the positive charge. Like ammonium, for example, is +1. So let's go ahead and take a look at BH3. This is an example of an incomplete octet. So you need to remember that over here. So boron, if we take a look at it in our periodic table, is in group 13. So it has 3 valence electrons. So we're going to do 3 plus 3 times 1, because there's 1 for each hydrogen there. We're going to have 6 electrons to place. So what we're going to do now is we're going to go ahead and connect our boron to our 3 hydrogens. And so what we did is we placed 6 electrons total, because there's 2 in each line. So 6 electrons minus 6, there's 0 left. And so our hydrogens are happy, but then you'll say, well, oh no, there's only 6 valence electrons left in the boron. We need 2 more, so let's create a double bond and somewhere and get a full valence shell. Well, first of all, we can't really do that because there's no lone pairs on anything to create double bonds with. And secondly, you don't need to because this molecule is stable the way it is with an incomplete octet as BH3. So it doesn't matter if there's even if there were lone pairs. Let's say these were fluorines instead with lone pairs on them, you wouldn't take and make it a double bond because boron is more stable without the double bond. It has to remain as a stable octet. So that there would be an example where you wouldn't have to create a double bond and you would just need to remember that. Now, let's get to the second example of incomplete octet, beryllium hydride. So here we have 2 valence electrons and 1 for each hydrogen. So it's 2 plus 2 times 1, which is 4. So we'll connect our beryllium central atom to the 2 hydrogens. And what you'll notice is you just placed 4 electrons because 2 in each line. So 4 minus 4 is 0. And normally you'd think, well, beryllium's not happy. I have to make double bonds. Well, first of all, you can't because your peripheral atoms don't have lone pairs. And even if they did, you wouldn't want to do that because beryllium is perfectly happy with just having the 2 bonds or the 4 valence electrons. So 2 bonds, 4 valence electrons is good for beryllium. 3 bonds or 6 valence electrons is good for boron. Now we're going to take a look at the expanded octet examples. And that'll cover it for the Lewis dot diagrams. And you need to make sure you practice because you want the Lewis dot diagrams to become second nature. As we're going to go into VSEPR after, and VSEPR requires a good knowledge of Lewis dot diagrams. So this is an expanded octet, and you'll see that as we go through it. So sulfur has 6 valence electrons, and fluorine has 7. So that's our total of 6 plus, there's 7 for fluorine times 6 there. So it's 42 plus 6, 48 electrons a place. And so our central atom is going to be sulfur. It's less electronegative, but there's also only 1 of it, so that works as well. And we're going to place our fluorines around sulfur. There's 6 fluorines a place. So I put 1, 2, 3, 4, 5, and 6. And so what I've done here is I've actually placed 6 bonds, right? So 1, 2, 3, 4, 5, 6 bonds, which means I've already placed 12 electrons. So there's 36 left to go. And so I'm going to start filling in my my peripheral atoms with the lone pairs. And it looks like each of them needs 6 more electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So that leaves me to 0. And so it looks like all the fluorines are happy. And if you look at sulfur, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 valence electrons. And you might think, oh, I made a mistake. No, you didn't. This one's allowed to have an expanded octet. You'll notice that sulfur is in period 3. So it just has an expanded octet. There's nothing really extra you have to do, but just realize that you didn't make a mistake there. And now we get to the example of H3PO4. This is an oxyacid. So in the case of an oxyacid, you'll notice one of the general rules we said was that the hydrogen bonds to the oxygen. So we'll choose a central atom, and a good central atom to have is the one that there's less of again, P. So I'm going to write that down here, P. And I'm going to count all my valence electrons. So 1 in the hydrogen, 5 in the phosphorus, 6 in the oxygen there. And so that's going to be 3. So that's 3 times 1 plus 5 plus 6 times 4. So that's 24 plus 3 is 27. So that's plus 5, 32. 32 electrons. And so we're going to connect all the O's to the phosphorus. And then we're going to connect the H's to the O's. And so what we've done here is how many bonds do we have? We have 1, 2, 3, 4, 5, 6, 7. 7 bonds. So we place 14 electrons. So what that means is there's 18 electrons that are left to place. And so what we can do is we can start placing our 18 electrons around our atoms that still need to be filled here. So we can go like this. We can say we need 1, 2, 3, 4 on this oxygen. That one's happy. 1, 2, 3, 4 on that oxygen. That one's happy. 1, 2, 3, 4 on that oxygen. That one's happy. And then I made these images a bit too close to each other. Let me just erase this here. I'm going to make them a different color so you can see that they belong here. So 1, 2, 3, 4, 5, 6. I'm just going to draw back the old electrons in a previous example so you don't think they just disappeared. That. So we placed a total of 18 electrons, which means that we are done here. And this one here would not necessarily be an expanded octet because we only have our 4 bonds surrounding it. But what's different about it is that it's often difficult to tell where you put the hydrogens, and you really need to place them on the oxygens because they are valence, they are oxyacids. The other thing I want to mention is that this could be an expanded octet. Some students may have drawn this as a double bond, so they may have said, you know what, I'm going to make this shared in here and make it a double bond. If you left it like this, it would be acceptable right now. But generally speaking, when you have oxygen bonded to central atoms and there's no charge on a molecule, it's typically more stable when you have a double bond or 2 bonds to it. So this is actually the better structure. Notice this oxygen has 2 lines, this one has 2 lines, this one has 2 lines. And so to make it a better structure, you can just make those electrons shared in there, and you can have a double bond there. And this works, so you can have an expanded octet this way because phosphorus is in period 3. So generally, if there's no charge on the molecule and you have oxygens around, the oxygens typically do like to have 2 lines on them as it's more stable for them. So that there was a lesson on drawing Lewis structures. So you should be able to use these steps here to draw Lewis structures. Just remember that when you're counting the number of valence electrons that you want to add electrons if there is a charge, like 1 for negative, 2 for negative 2, 3 for negative 3, and then if there's a negative charge, I should say a negative charge. And if there's a positive charge, you remove electrons for each positive charge on the ion.